Well, good afternoon. Happy Wednesday. So what I'd like to do today is talk about acid rain and visibility. So we're starting a unit where we'll look at a number of specific problems pertaining to air pollution. So in this lecture, we'll look at issues regarding acid rain. We'll look at pH of rainfall. We'll look at the effect on vegetation, water bodies, surfaces, and we'll also look at visibility issues. So just a reminder in terms of pH, pH is the negative log of the hydronium concentration, that is H+, and waters that have a pH less than 7 are considered acidic. The POH is the negative, and I forget, it should be a negative here that I missed. I apologize. The negative log of the OH minus concentration, and waters that have a pH greater than 7 are considered alkaline. Waters that have a pH of 7 are considered neutral. And I've just given you the equilibrium expression for the dissociation of water to H+ and OH-. So I've got the equilibrium expression for that reaction. Now, the natural pH of rainfall is actually 5.6. And we showed that in an earlier lecture, and it was because of the dissolution of CO2 in the gas to CO2 aqueous, and then that CO2 aqueous reacts with water to produce carbonic acid. So it's because of that pH of natural waters and rainwater is about 5.6. Now what you see, these are data collected back in 1985. So you see that for much of the east coast of the US, the pH was less than a 4.5, in some cases less than 4.1. So we've got significantly acidic waters, not as much in the western part of the US. Does anyone know why? Why is this situation, or why did this situation occur?
The population is less dense.
One, the population, there's denser population on the East Coast. So got a denser population, which means what?
More energy used.
More energy use, okay. More energy production.
Coal, right?
Coal, okay. Most of the coal that is burned or was burned at the time in the eastern half of the US was high sulfur coal. So the coal that's mined in West Virginia, much of it's mined right in this region here. So West Virginia, Southern Ohio, and Kentucky is high sulfur coal. Most of the most of the coal that is mined out in the West is low sulfur coal. So you've got low sulfur coal here, you've got high sulfur coal on the East Coast. And you've got and at the time, there were a significant number of coal-fired power plants burning that low sulfur coal. Now, what happened was, because of the sulfur in the coal, there were significant emissions of SO2 and also emissions of NO and NO2 from the power plants. Those react in the atmosphere. OH radicals are produced from a variety of reactions, and those are present in rainfall. They're in water in clouds, water in the atmosphere, fog. They react with the SO2 and the NO2 to produce sulfuric acid and nitric acid. And then that nitric acid can either be deposited on structures, on plants, in water, either from rainfall, so dissolve into the rainwater and then deposit that way. They can also deposit in fog, or the SO2 and the NO2 particles can deposit as dry deposition. So it can either deposit as the particle form and then react on the surface of the structure or the plant or in the water, or it deposits as what we refer to as wet deposition in rain or fog. The reaction of SO2 to form sulfuric acid is catalyzed by metals, and coal has a variety of metals in the coal itself. So the emissions from coal can also have a significant amount of metals present if they're not removed from treatment technologies. The presence of peroxide, hydrogen peroxide, and OH radicals, which can be present in rainfall, will also catalyze these reactions, as do oxygen and water. The reaction of NO2 to form nitric acid is also catalyzed by OH radicals, and this is predominantly during the day, and it will react with ozone at night. So the reactions vary depending on the amount of sunlight that is present. HCl is actually the result of the transport of Cl- from the stratosphere. Early in the course, I mentioned how initially scientists thought that there was no transfer of pollutants from the troposphere to the stratosphere. They learned that that was not the case, and there actually is transport both to the stratosphere. We'll talk about fluorocarbons and how those are transported to the troposphere, but there's also the transport of chloride from the stratosphere back into the troposphere. Now, when acid rain comes in contact with vegetation, it can have a number of effects. This includes what is referred to as necrosis, which is the death of tissue. So this is a severe, you can see it here, where you actually see a destruction, death in the tissue. Chlorosis is the loss of chlorophyll. And you can see that here, where you would expect the leaves to be a much darker color. They're more a yellow color, and that's because the loss of chlorophyll, you can see that in this leaf here too. So as you can imagine, loss of chlorophyll affects photosynthesis, which affects plant growth. So that results in growth abnormalities. This also has an economic effect, because if your crops die, then that's a significant loss of income because of that. And then lastly, we see needle dieback. You see that here, what happens here is the acid forms a film on the needles of pine trees. It actually dissolves the waxy coating on the pine needles, and that prevents the pine needle from holding in water, from retaining water. So what happens then is you get desiccation of the leaf or the needle, and that results in the death of the tree. And that's what you're seeing in this image here. So all of those dead trees are the result of acid rain. And this was a significant problem in the Adirondacks, for instance, in New York State. So if we go back and we look at this map here, much of this region here has granite outcrops. Because it has granite outcrops, it doesn't have, the soil doesn't have much buffering capacity, and the waters don't have much buffering capacity. So as a result, the impact of acid rain was very significant in these regions. So for instance, New York State, Vermont, New Hampshire, parts of Maine, parts of Ontario, much more significant than it was, for instance, in Michigan, where our waters have a much higher buffering capacity, a much higher alkalinity, because of the presence of a limestone that outcrops within this structure. Acid rain also affects the soil acidity. So as you can imagine, if the rain is more acidic, that water can percolate down into the soil. It can also percolate down into the groundwater, resulting in more acidic soil water, more acidic groundwater. Because the water is more acidic, it reacts with the minerals and it starts to dissolve the minerals. So what will happen here is, for instance, you'll see a change in the ratio of calcium to magnesium. And that calcium to magnesium ratio is important in terms of maintaining proper nutrient assimilation in the root system. It's also important, for instance, in terms of maintaining proper calcium uptake in mollusks. So this decrease, what happens is the calcium concentrations are increasing at to a greater extent. Yes, I'm sorry, not sure what I said. Should say calcium aluminum. So yes, I did mean calcium aluminum. So at this calcium aluminum ratio will decrease. So calcium is going to dissolve to a lesser extent than aluminum at the same pH decrease. So you'll see this decrease in calcium aluminum ratios, resulting in a disruption in the nutrient assimilation in this root zone here, or in the uptake of calcium by mollusks in the water body. The other problem is that if there is any metal deposition, so for instance, as I mentioned, the emissions from a coal-fired power plant can also contain metals. So those metals, if they dissolve, they can be released both to the groundwater or to the soil, resulting in contamination. The other issue is, for instance, if biosolids are applied as a fertilizer, those biosolids, if they contain metals, those metals can also be solubilized and then released to the groundwater or the surface water. Any questions so far about these impacts of acid rain? And thank you for catching me on, I'm not even sure what I said on the calcium aluminum ratio.
No worries. I think you said calcium, magnesium instead.
I apologize. Don't ask me where that came from. Actually, probably because calcium and magnesium are often so associated with one another. When you talk about hardness, it's always calcium and magnesium. So I apologize. The other issues that, and this was observed back in the 70s and the early 80s, when acid rain was a very significant problem in the US, in Ontario, and also in the Scandinavian countries, Poland, parts of Germany. They observed this decrease in pH in the bodies of water, observed an increase in the aluminum concentration, as you can see here, and that resulted in a significant decrease in the fish population. One of the problems is that the aluminum concentration actually irritates the fish gills. They cause the production of a protective mucus. But the problem is that protective mucus then inhibits absorption of salts, the transfer of oxygen, and the fish suffocate. So what they observed in this lake back in the late 70s was a significant decrease in the population of young fish. Basically, the fish were dying out. Another problem is because of the change in the acidity of the water, or the pH of the water, that resulted in a failure of reproduction. So in many cases, the eggs just didn't hatch. And as I mentioned, it inhibits calcium uptake in mollusks. So you're not going to get the growth of the mollusks, which you need for a healthy ecosystem. It wasn't just plants that were affected. It's also stone surfaces. So it's also metal structures. The presence of, or the combination of hydrochloric acid and SO2 is about 20 times more reactive than SO2 alone. The other problem is that we mentioned the CO2 dissolving. We have carbonic acid, bicarbonate, and carbonate, or our three species of carbonate. If the pH is lower, that shifts equilibrium toward carbonic acid. And that carbonic acid can then react to result in significant corrosion of your concrete structure. The other thing that happens is that SO2 can react with calcium carbonate. That forms, so we need oxygen and we need water, and that reacts to form gypsum and releases CO2. So we're producing more CO2. That CO2, if we have water present, produces more carbonic acid, And it's this vicious cycle that results in the corrosion and destruction of the concrete. And you can see the rebar now exposed because of that. The gypsum is more soluble than the calcium carbonate, and so that actually gets washed away, exposing, as you've seen it here, the rebar. SO2 with water also reacts with solid particles that contain trace metals. And then what happens is you get electrochemical corrosion of iron and steel. And you can see it here. These green streaks are actually the result of the oxidation of copper, and it's just washing away that material. This is accelerated by the presence of sulfate and chlorides. So where you have sulfates and chlorides, you're going to see a more rapid corrosion of your metal structures. And of course, oxygen is a strong oxidant, and presence of oxygen, which we need, also accelerates these corrosion reactions. Because of the
Professor, could you go back to the last slide for 1 sec?
Sure.
Thank you.
Any questions?
No, I just need to see the two molecules.
So I've mentioned that acid rain is resulting in the formation of SO2 and NOx, and NO and NO. Those result in the formation, as we mentioned, sulfuric acid, and it's not shown here, but also nitric acid. Those gases can nucleate. What does that mean? Anybody as a kid do an experiment where you make a really high concentration of sugar, and then you put a string in the concentrated solution of sugar. Nobody do that? There's a little experiment for you to do when you're home. What happens is the sugar will actually crystallize on the string. The string actually provides the nucleation energy to allow what is dissolved sugar to actually crystallize. So what can happen is you get essentially this crystallization. Now that can be, you can have a particle that can provide that nucleation energy, but you get nucleation, and then you produce these ultrafine aerosols. Those ultrafine aerosols can attach to one another, so they can coagulate to produce now fine aerosols, and can further react even to produce coarse aerosols. These aerosols can move deep into the lungs, and what you see is an increase in morbidity, which is illness, and mortality from lung disorders. You also see an increased incidence of asthma and bronchitis as a result of the release of these chemicals, the SO2 and the NOx, then resulting in increased rates of asthma and bronchitis. There have been a number of studies looking at the effects of, talk about the acid rain program. We'll talk more about that when we get to the Clean Air Act, but the acid rain program was a cap and trade program that was developed to reduce the emissions of SO2 and NOx predominantly from industrial facilities and coal-fired power plants. The public health benefits of the acid rain program are valued at roughly $50 to $65 billion per year due to decreased mortality, decreased hospitalizations, and decreased emergency room visits. In terms of cost benefits, the benefit cost ratio for the acid rain program has been estimated to be 40 to 1. So the benefits are 40 times greater than the cost of this program. So extremely successful program and has resulted in significant reduced illness and deaths as a result. So where are we right now with respect to acid rain? You don't hear it in the news. We used to hear it all the time. You don't hear much about acid rain anymore. Well, in terms of SO2 emissions, back in 1980, and we don't have much data before 1980, but back in 1980, you see that the concentrations, your average concentration was about 150 parts per billion, and my pen is acting up. And you can see that we have reduced it very significantly. The latest data we had that I could obtain was for 2019, but you see roughly a 92% decrease in the average SO2 level. You see that the range was very significant, from about 50 to probably about 260 parts per billion back in 1980. It would have been even higher before that. And you see we're in the range from 0 to 20 part per billion now. So very, very successful in terms of reductions. Now, in terms of emissions, you see actually quite similar results, about a 91% decrease in emissions. Significant emissions decrease right in here. It's pretty steady before that. So see a decrease here. You don't see much change from about 1995 to 2005. And then you see a very significant decrease here. Anybody know what happened between 2005 and 2000?
Do we start using natural gas more and more?
Exactly. Two things happened. One, the recession, and that did have a resulting decrease in emissions just because people were concerned about the cost of energy. So you see some decrease for that reason, but a very significant change from coal to natural gas. Natural gas becomes much more economical. So you see that switch from coal to natural gas. And that is continuing to decrease. You also start seeing more renewables. So it's that combination from coal to natural gas and then the increase in the renewable energy production that you see such a significant decrease in SO2. These are the various regulations. So the original set of regulations, I mentioned cap and trade. Like I said, we'll talk more about what that means in the clean air unit, but that had a significant impact in reducing SO2 emissions. There was also the Clean Air Interstate Rule for a period of time. That comes in about 2005. That rule was vacated in the courts. It was argued for several years in the courts. And then ultimately in about 2015, that morphed into the cross-state air pollution rule. The last set of amendments to the Clean Air Act were in 1990. And as I mentioned before, everything after that has been, every set of regulation has been developed as a rule. So EPA is predominantly doing rulemaking in part because the legislation isn't being passed to amend the Clean Air Act. You can see here decreases in emissions of the power sector. So this is the electric power sector. You see very, very significant decreases in SO2. not expected to change much over the next 20 or so years. Same thing with NOx. The expectation is that it's not going to change. What we haven't had a significant impact on is CO2 in terms of where we need to go, not really with acid rain as much, but where we really need to put our emphasis is on how do we decrease the CO2 emissions. And that will be a mix of renewables, hopefully getting to the point where we can sequester the CO2, and just looking at new technologies. And you can see this change here. You can see if we look, even this is just 2010 and kind of where we are right now, you can see that the amount of coal consumption has decreased significantly. Back in the previous 4 years or so, and the whole discussion of clean coal, and are we going to kind of increase or reinstitute coal burning, that wasn't going to happen. Why? Anybody know why do I say that that wasn't going to happen? MSU switched to natural gas. Why wouldn't MSU decide suddenly to switch back to coal?
Is it becoming less economical?
One, economics, okay? One of the reasons why MSU switched to natural gas had to do with treatment, the cost of treatment. The mercury regulations became very stringent, and that meant costly treatment technologies. So if you stayed with coal, you needed to institute and implement the technologies to reduce mercury emissions. So that was one reason. Why else? Once you've switched, what's the difference between natural gas and coal from a physical perspective? One's a solid fuel, one's a gas. So the whole technology for feeding that fuel into the boiler is different. Okay, you don't need to store it. You don't need the conveyors. But the way you inject coal, the coal dust versus gas is entirely different. So once you switch from a solid fuel to a gas fuel, going back isn't trivial, and it's costly. So the whole idea that suddenly we were going to switch back to coal wasn't going to happen. There's just no way it couldn't happen, because these power plants would have had to completely restructure their fuel delivery system. If that makes sense. How come nuclear isn't as popular? One of the major reasons nuclear isn't popular in the US is 3 Mile Island. 3 Mile Island was a nuclear power plant located along 287, I think, in Pennsylvania, kind of in the almost middle of Pennsylvania. It had a release of radiation back. It would have been, I was in graduate school at the time. I used to pass by it every time I drove from New Jersey to West Virginia, probably in about 1980. And between that and then Chernobyl, exactly. Between 3 Mile Island and Chernobyl, it pretty well killed the nuclear power industry. And then the question of how do we store the radioactive waste product from the nuclear power. And then Fukushima didn't help even thinking about it. I mean, that major accident, the result of an earthquake and a tsunami. So dealing with these large accidents really had a detrimental impact on nuclear power. In terms of CO2 emissions, one could argue that it makes significant sense, but then there's the issue of radioactivity. It's a good question. We haven't built a nuclear power plant in the US in, I don't know how many decades. It's probably at least three and a half decades. NO2, we haven't been anywhere near as successful in reducing NO2 emissions as much as we've reduced SO2 emissions. You can see it here. These are ambient concentrations, and I don't think I mentioned that before. So they're not emissions, but they're ambient concentrations. You see we're well below the standard, but again, we haven't been able to achieve the reductions. One of the major reasons for that is most of the SO2 emissions are from stationary sources. It's much easier to control emissions from a stationary source than it is from a mobile source. Most of the emissions from NOx are actually from vehicle emissions. And it's just much harder when you're talking about millions and millions of vehicles on the road versus a few hundred power plants to control those emissions. The other issue with NOx is when we looked at combustion reactions, we said that we had perfect combustion. So we said that we were just producing CO2 and water. However, there's no such thing as perfect in real life, and we don't have perfect combustion. And what we produce is thermal NOx. Thermal NOx results from the reaction of N2 in the air with the oxygen. So this is from the air. So we supply oxygen. That results in the formation of NOx. So this reaction occurs at high temperature. We produce NOx. We can also produce fuel NOx, which is the reduction is the oxidation of nitrogen in the fuel. So this is any nitrogen in the fuel gets oxidized to form NOx. And then we have what is referred to as prompt NOx. And this is the result of nitrogen in the atmosphere, again, and free radicals that are produced in the flame and result in the formation of NOx. We'll talk more about this later when we talk about combustion, but because of these different reactions, makes it more difficult to control NOx emissions. And you can see that here. We have achieved significant reductions in NOx, but again, not as great as we achieved with SO2. And the same program, the acid rain program, the Clean Air Interstate Rule, and the Cross-State Air Pollution Rule have all been promulgated in order to reduce these emissions. So where are we? Let's give you some comparison. If we look at the pH of rain, so going back to where we were in 1985, to the most recent map that I could obtain was in 2018. You see that most of the US is now pretty green color. So we have significantly reduced the acid rain problem in the US. Significantly reduced the amount of nitrate in rainfall. Again, looking from 1985 to 2008. We've reduced the amount of sulfate. You can see how bright red this was here. And now most of the country is pretty much a dark green. So we have had a very significant impact. The acid rain program has been very, very successful in reducing these emissions. Lastly, I just want to mention visibility briefly. And visibility is a measure of the aesthetic value and the ability to enjoy scenic vistas. It's basically the greatest distance that an object can be seen. So you can talk about a visibility of a mile, 3 miles. It's important because it's also an indicator of general air quality. Particulates, including aerosols, will impact what we refer to as the visible range. So particulates, aerosols will impact what we refer to as visual range. And NO2 is the one pollutant that absorbs light. I've got a series of photos just to kind of give you a sense of this. This is the Grand Canyon. On the left, you see a photo where the visual range is almost 400 kilometers. On the right, a photo where the visual range is roughly a tenth of that. The reason for the decrease is air pollution. We also talk about haze. Haze is the condition where dust, smoke, and other predominantly dry particles obscure the clarity of the sky. And you can see it here. This is in the Great Smoky Mountains. On the left, you've got a clear day, in the middle, moderate haze, and then a really hazy day where you can't see much of anything. What happens is humidity tends to magnify the problem because some particles attract water. So then they grow in size, and as a result, they scatter more light so that you decrease the visibility. And that's what's observed here. We also talk about layered haze. We'll talk about a thermal inversion, but you can see kind of this haze right in here on the horizon. See it right here. So what happens is, in this type of a situation, it tends to be cold air trapped by warmer air and then cold air above it. So that's your thermal inversion. And those pollutants just sit close to ground level. And when you look out at the horizon, it looks like this layer of haze at the horizon. Uniform haze, what happens is this inversion starts to break up and you get more mixing. So the pollutants become more dispersed throughout the atmosphere. And then we talk about opacity. And this pertains to the plume itself. So it's the amount of light that's attenuated by the plume. It's actually used because it can very easily be monitored. So it can be done on a continuous basis. And what is done is you're actually monitoring how much light can pass through that plume. And the regulations in Michigan state that the opacity cannot exceed 20% except for 1 6-minute period per hour, and still can't exceed 27%. And this image gives you a sense of what 0%, 25%, et cetera, opacity really means. So particulates are resulting in the amount of light that's attenuated. Water vapor can affect opacity, but it's exempt from these rules. And typically what you see with water vapor is you see clearly visible boundaries of your plume. And the plume tends to disrupt very abruptly. And you can see it here. If there's particulates, you'll tend to see more of a tan color in the plume. This is really, I've only got a minute left, so it might take a little bit longer, but this is basically just a series of photos. Whole question of, is it smoke, dust, haze, fog? What is this? And I've just got a series of photos to show you. This is haze. It's in Kuala Lumpur. So you're talking haze, you're talking about dry particulates. This is a heavy haze in Indonesia. It was actually caused by wildfires. So wildfires are quite a distance. It's really the particulates that are resulting from the wildfires that scatter the light and cause this kind of orange, strange color in the sky. This is smog. This is right around the time that we formed the EPA, passed the Clean Air Act. It was not uncommon for the skyline of New York City to look like this. Combination, we'll talk about this in terms of chemicals, particulates, ozone, that resulted in this smog. Smog in Beijing, similar, again, the same. We'll talk about this photochemical smog and how that occurs and why it's so hazardous to our health and well-being. This is smog in Mexico City. You can see kind of this during an inversion, and you can see that pollutant's just sitting close to the ground level. This is fog. This was taken a few years ago on a trip to Cadillac Mountain where we were hoping to see the sunrise. This is what we got to see. We did not see much of a sunrise. We got to see lots of fog, just water vapor, basically up in the clouds. Fog on the Golden Gate Bridge. And then this is mist. Mist is very similar to fog. It's just lower amounts of water vapor. And again, this is taken from Cadillac Mountain in Maine. And then we have smoke. This was taken actually out in Washington and during the forest fires, and what you actually see in the background is the smoke from the forest fire. Similar, these were all taken on that same trip, and it was kind of bizarre as we were driving through and not quite knowing where we were going to find the fires and how far we could actually even drive. And you can see more of the fires kind of in the background. These are dust storms. Beijing is not far from the Gobi Desert, and it's not uncommon to have these massive dust storms. This is not fog. It's actually naturally occurring, although it's gotten worse because of desertification. And then this is photos from a dust storm on the Arizona, New Mexico border. So stop there with and I apologize for going over a bit today. Happy to answer any questions you may have about acid rain or anything pertaining to class.